In April 2026, the Artemis II mission lifted off from the Kennedy Space Center, carrying a human crew into a high Earth orbit before firing its engines to swing around the far side of the Moon. This was the first crewed voyage to the lunar vicinity in over 50 years. The crew aboard the Orion spacecraft was composed of Commander Reid Wiseman, pilot Victor Glover, and mission specialists Christina Koch and Jeremy Hansen. This mission marked Koch as the first woman, Glover as the first person of color, and Hansen as the first non-US citizen to travel into deep space. The flight was a rigorous systems validation. By flight day 4, the crew was executing manual proximity operations and piloting overrides, providing the data necessary to ensure human control if automated systems fail during future dockings. Shortly after, they flew directly into a 40-minute communications blackout as the Moon obstructed their signal from Earth. When they reacquired the signal, the crew had set a record distance of nearly 253,000 miles from Earth. During the flyby, they mapped 2 previously unnamed craters and captured high-definition data on the Sun's outermost atmosphere during a perfectly aligned solar eclipse. Artemis II proved the hardware works and humans can navigate cislunar space. However, maintaining a human presence in orbit for a few weeks is a vastly different engineering challenge than supporting life on the lunar surface for months at a time. To build a permanent surface base, NASA originally planned to construct the Lunar Gateway, an orbiting space station that would serve as a staging point. However, engineers found that forcing landing vehicles to rendezvous with an orbiting station introduced severe fuel penalties and complicated flight trajectories. This bottleneck led to a policy correction in March 2026. Under the Ensuring American Space Superiority Executive Order, newly appointed NASA Administrator Jared Isaacman paused the Gateway Station to prioritize a permanent ground presence. This diagram illustrates the mechanics of the pivot. Instead of burning fuel to align with an orbiting station, landing vehicles now bypass it. They shift to a direct docking profile in an elliptical polar orbit, simplifying the descent. Bypassing Gateway freed $2.6 billion, redirecting capital from orbital logistics toward ground infrastructure, specifically pressurized habitats and nuclear grids at the South Pole. Securing this 3-phase ground strategy required massive financial backing. Despite administrative efforts to transition toward private rockets, Congress passed the act in 2025, providing $4.1 billion specifically to keep the government-led heavy lift program on schedule. NASA traded the visibility of an orbiting space station for the operational efficiency required to drop thousands of kilograms of cargo straight onto the lunar South Pole. The engine driving this direct-to-surface pipeline is the Space Launch System, or SLS. It is currently the only operational vehicle capable of throwing a crewed capsule directly towards cislunar space. To achieve an annual launch cadence, NASA standardized the SLS Block 1 configuration. By using refurbished RS-25 engines from the Space Shuttle fleet and a standardized rocket stack, the agency can maintain a predictable production cycle across its industrial partners. Sitting on top of that rocket is the Orion spacecraft. It relies on the European Service Module, which handles propulsion and carries enough life support consumables to keep a 4-person crew alive in deep space for up to 21 days independently. For the final descent, NASA awarded contracts to 2 providers to avoid a single point of failure. SpaceX is developing a modified version of Starship optimized for the lunar vacuum, while Blue Origin is building the Blue Moon Mark II, a reusable lander designed for a 30-day surface lifespan. These massive landers require a complex propellant chain. Because they burn through their fuel reaching orbit, they must be refilled by multiple tanker flights before heading to the Moon. This challenge forced NASA to downgrade the 2027 Artemis III mission to a docking and fuel transfer test in Earth orbit. Launching a rocket is an established capability. The current hurdle is building the industrial-scale logistics chain required to move massive quantities of cryogenic propellant across the vacuum of space. Once that propellant chain is validated, the program moves to Artemis IV in 2028. This is the point where humans will physically touch down to begin deploying the first permanent surface assets. Look at this technical breakdown of the Axiom AxEMU spacesuit. It uses a modular design to fit 99% of the population, providing the flexibility required to perform geological sampling. Its outer layer was engineered specifically to withstand the abrasive dust and extreme thermal gradients found at the South Pole. Before humans can build a long-term habitat, they must locate volatiles. The Viper rover will scout shadowed craters using a neutron spectrometer system to detect hydrogen, an indicator of water ice, up to a meter beneath the regolith. Surface mobility will evolve from open-air buggies to the JAXA Toyota pressurized rover. Known as the Lunar Cruiser, this vehicle functions as a mobile laboratory where astronauts can live and work up to 30 days without wearing spacesuits. These assets change the nature of the mission. Astronauts arriving at the South Pole in 2028 will have the mobility and protection to move past the landing site and establish a continuous presence. This map details the lunar South Pole. While containing valuable ice, it features permanently shadowed craters where solar power is ineffective. To survive the 14-day night, NASA will deploy Lunar Reactor 1 in 2030, providing constant electricity to keep habitats powered. There is a geopolitical urgency to this deployment. Through the Artemis Accords, the United States and over 60 partner nations are establishing the norms and infrastructure needed to secure these resource-rich zones. This schematic details the SR-1 Freedom spacecraft, launching in 2028. It uses a 20-kilowatt microreactor for nuclear electric propulsion. Constant, high-efficiency thrust significantly shortens the transit arc between Earth and Mars, minimizing crew exposure to cosmic radiation and physical degradation. Operating a permanent base in the South Pole's shadows provides the data needed to solve the mechanical and physiological challenges of surviving on Mars. By standardizing heavy-lift rockets, mastering cryogenic refueling, and deploying orbital nuclear reactors, the Artemis campaign is building the logistical bridge required to reach the Red Planet.